So in this video we want to establish the uniqueness of matrix inverses, or in other words we want to identify that if a matrix has an inverse, that inverse must be unique. There can't be two different inverses for the same matrix. So we have a little theorem here, uniqueness of matrix inverses. It says if a matrix has an inverse, the inverse is unique. So the proof of this, what we want to start off is by just making a generic matrix A. So we're going to say let A be and then matrix inverses are only defined for square matrices. So we want to make A square matrix. So let A be an n by n matrix. That forces it to be a square matrix. And we're going to suppose that it has an inverse. We'll suppose the inverse exists. Not every square matrix has an inverse. Inverse doesn't necessarily need to exist, but we're going to suppose it does. So let A be an n by n matrix and suppose, and we want to show that it's unique. We want to show the inverse is unique. So what we'll do is suppose that we found two of them. And suppose A sub 1 inverse and A sub 2 inverse are both inverses of A. So what we do is we suppose there's two different inverses, and then what we want to demonstrate is that they must be the same matrix, that the inverses must be equal to each other. So we want to note that when we multiply a matrix times its inverse, so A sub 1 inverse, that it equals the identity matrix. So if I have an n by n matrix A, then A times A1 inverse, where the 1 here is just identifying that this is a different inverse than the one subscripted A sub 2. So we would subscript the I, which is the identity matrix, with the n, saying it's the n by n identity matrix. So note that A times its inverse equals the identity matrix, but because A sub 2 is also an inverse, we know that if we multiply A times A sub 2 inverse, that will also get the identity matrix for n by n matrices. And if both of them are equal to the identity matrix, then by the transitivity of equality, it follows that they must be equal to each other. So it follows that it must be true that A times A sub 1 inverse, which equals the identity matrix, must equal A times A sub 2 inverse. So we have A times this first inverse equaling A times the second inverse. And then what we do is we take either one of these two inverses that we've identified, it doesn't matter which one, we just multiply both sides by that inverse. And then we want to remember that order of multiplication matters. So if I multiply this on the left hand side, by A sub 1 inverse, then over here I have to have the A sub 1 inverse. If I'm multiplying both sides by A sub 1 inverse, I must also have it on the left hand side, because matrix multiplication isn't commutative. So if I put it on the right, they would need to be on the right over here. If I put it on the left over here, I have to put it on the left over here. And then we want to remember from properties of matrices under multiplication and addition that matrix multiplication is associative. So we can regroup the left hand side as A sub 1 inverse times the A times A sub 1 inverse, and we can regroup these two terms using the associative property of multiplication for matrices. We regroup this. And then we want to recognize that A sub 1 inverse times A has to be the identity matrix, because when you take the product of inverses, you get the identity matrix. The product of inverses gives you the identity matrix. And when we multiply the identity matrix times A sub 1 inverse, it's going to preserve the identity of A sub 1 inverse. identity matrix times the matrix A sub 2 inverse preserves the identity of that matrix. And now we see that the two matrices must be the same. They're equal to each other. So this is what drives the proof. We suppose that there's two of them, and then show that if we suppose there's two, they actually turn out to need to be the same matrix. So then we draw our conclusion. Because A sub 1 inverse equal to A sub 2 inverse, matrix inverses must be unique. And we can claim this because when we tried to show there's two of them, we discovered that they were just the same matrix.